Dear students, in this session, we'll learn about aromatic hydrocarbons. We studied about unsaturated, saturated and unsaturated hydrocarbon, and that carbon-carbon single bond, carbon-carbon double bond, and carbon-carbon triple bond. Next is aromatic hydrocarbon. Aromatic hydrocarbon, name itself indicates it is an hydrocarbon. It's a type of the class of an hydrocarbon. Okay. In this aroma, characteristic smell, aroma, pleasant smell or characteristic smell. And these are also we call as arene, A-R-E-N-E, arene. Aromatic hydrocarbon are the hydrocarbon having a characteristic smell or the pleasant smell. The compounds will be having means hydrogen. The binary compounds of carbon and hydrogen will be having a characteristics at pleasant smell are called aromatic hydrocarbon. Will be consisting least one benzene ring. Aromatic hydrocarbon also known as arenes. Arenes. Okay. Arene is nothing but least one benzene ring. Least one benzene ring, that is an aromatic hydrocarbon. These compounds are called aromatic hydrocarbon because the most of them possess a pleasant odor. Pleasant odor, this is derived from a Greek word aroma, means pleasant smell. So these will be after the burning will give a characteristic smell. Hence, these are we call as aromatic hydrocarbon. Most of such compounds are found to contain benzene ring, least by 6-membered carbon in cyclic group and will be having the alternative pi bonds in it. These are we call as aromatic hydrocarbon. And this aromatic hydrocarbon consisting the benzene ring are known as benzenoids. Known as benzenoid. What is benzenoid and non-benzenoid? Aromatic hydrocarbon containing the benzene ring or benzenoid. Few of the aromatic compound means will be having the alternate double bond or conjugated pi system. In that doesn't consist the benzene ring, those are we call as non-benzenoid. Non-benzenoid. So aromatic hydrocarbon in the two group. One is benzenoid, another is non-benzenoid. Benzenoid are those will be consisting the minimum benzene ring. Minimum benzene ring. Non-benzenoid are also having the conjugated pi system but doesn't consist benzene ring are called non-benzenoid aromatic hydrocarbons. Aroma means good fragrance. So define the structure of benzene. Benzene was isolated by Michael Faraday, but what happened after the isolation of benzene, the prediction of structure is the most complicated thing. Why? Because benzene, what we get from the qualitative as well as quantitative analysis, we found that we come to know that its molecular formula is C6H6. And this molecules and the molecular formula, it will be suggested that and will be having carbon-carbon unsaturation is nothing but may it consist carbon-carbon double bond or may it consist carbon-carbon triple bond. Before getting of the proper structure, before the getting of structure, there will be huge problem, highly problematic. Why this? Because we'll be studying step by step. First one, from qualitative and quantitative analysis, we come to know that we got the prepared benzene. So prepared by Michael Faraday, isolated, separated from Michael Faraday. And we come to know that its molecular formula is C6H6, 6 carbon and 6 of hydrogen. Okay. And there's reaction, why it makes it complicated. To check the degree of unsaturation, we'll do the test is called benzenoid test. Ozonoid test. Ozonoid test. Ozone, treat with ozone, will be forming ozonoid. and from that we'll come to know that the saturated means unsaturated compound where the double bond will be present. So when benzene is subjected to ozonolize, is benzene is treated with the ozone, will be it gives triozonoid, which gives triozonoid, three group ozone means O3 oxygen will be attached to 3 carbon. It indicates that it will be contains 3 double bonds, means out of 6 member carbon, so 3 carbon will be consisting carbon carbon double bond, but it did not decolorize bromine. We are in CCl4. So when we treat the bromine, means the brownish color, that when it is added, means in a case of unsaturation, it changes to a color from uh, brownish to colorless, but it doesn't decolorize bromine in CCl4. It indicates that it is not alkene, it is not alkyne. It is not alkene or it is not alkyne. From that we come to know that it is not carbon carbon single bond, it is not carbon carbon triple bond. It means carbon will be consisting the 3 bonds, means 3 carbon will be having carbon carbon double bond. So all these unsaturation means may it consist carbon triple bond also, but it disproves that benzene treat bromine treat with carbon tetrachloride CCl4. So we'll be getting, so benzene when treat it CCl4, here the bromine attaches to this, as well as here 1,2 bromine, as well as if the bromine get attached to the same as it is 1 bromine, here bromine and here is bromine, 1,2 bromine and 1,2 bromine. So presence of double bond as well as absence of double bond, there will be addition of bromine will be takes place. Okay, so with ozonoid, with the treating of ozone, we come to know that it is in a triozonoid. It indicates that will be consisting 3 double bond, but it fails to decolorize bromine, fails to change this brownish color into colorless, is nothing but doesn't consist in triple bond. So it indicates that it is not an alkene or it is not an alkyne. So not an alkene means from this, from basic data we come to know that doesn't consist double bond as well as double doesn't consist triple bond. The problem is this, because from ozonoid we come to know that we'll be having the 3 double bond, means 3 unsaturated compound, double bond or triple bond, but it doesn't decolorize this bromine. From that we come to know that it doesn't have double bond and triple bond. So the problem arises here, if doesn't consist double bond and triple bond, how it will be the existence? So benzene was further formed to produce one and only a monosubstituted derivative, which indicates that all the 6 carbon with the 6 hydrogen atoms are identical. If the benzene are treated with the monosubstituted halogen derivatives, okay, when we treat with bromine, okay, what happened, we'll be getting the bromine can substitute. So I'll write here, so bromine can substitute this one alternate double bond, here is bromine, can substitute here also, can substitute here also, can substitute in this position ortho or in this position of an ortho also. So it indicates that whether it consists double bond or whether it is consists single bond in all these benzene, means in the ring of benzene will be consisting the hydrogen, all hydrogens are identical with each other. The hydrogens, all the hydrogen in 6 benzene ring or 6 of the carbons are identical with each other. Okay, so based on this experimental data, many of the scientists were trying to get the structure of benzene, but finally it was proved or explained by the Auguste Kekulé in 1865, he proposed the structure, the following structure. Okay, so based on the earlier data, so it will be having carbon carbon, it shows an addition reaction, substitution reaction, means hydrogens are identical with each other, because monosubstituted derivative will be getting all the 6 hydrogens are identical. Means from ozenoid, we come to know that we'll be having the carbon-carbon double bonded, 3 carbon double bonded compound. But it doesn't decolorize the bromine. It indicates that it's not an unsaturated compound. Means it's not containing double bond and triple bond. Again, the problem arises. With kept all this in mind, the scientists were trying in that time. The Auguste Kekule, the name of scientist, one day, every day all are curious about the structure. While he slept, okay, while he slept, he was thinking about the structure of the benzene. And the midnight, and while in his dream, he got an image, he got in a picture like a serpent tried to catch its tail. A serpent tried to catch its tail. This was a dream of the Kekule. Means he was dreaming like this. Then he come to know that means based on that the serpent tried to catch its tail. He thought that double bond. It doesn't have a fixed double bond. It doesn't have a fixed double bond. It may consist alternate double bond. It may consist alternate double bond. From the X-ray diffraction, we come to know that it's not having a single bond structure. It is not having a double bond structure. Means bond length are different. Then arrangement are different. So hence, he proposed a structure like this. These are the two structures. These are the two structure. In this, the first one, carbon will be having the double bond, alternate double bond. So 1, 2, 3 double bonds, and the hydrogens are identical with each other. So this alternate double bond, he come to know that while in his dreaming, what he saw, the serpent is trying to catch his tail. He is nothing but this double bond are rapid in movement. In first of means when we notice that in a second, 1, 2, and 3, 4, 5, 6. So number of carbon here also 1, 2, 3, 4, 5, 6. So 1, 2 will be having a double bond. 1, 2 carbon double bond. After a few seconds, this double bond will shift here. This become 2, 3. And this 3, 4 double bond, few seconds it shift to 4, 5. And 4, 5 double bond shift to 6, 1. So after a few seconds, 6, 1 double bond changes to 1, 2. We'll be getting again this structure. Then 1, 2 double bond turns to 3, 4. We'll be getting this structure. And 4, 5 double bond shift to 5, 6. We'll be getting this double bond. These two movement are rapid in movement. Means these two structure are rapid movement with each other. Hence, this is what we studied as resonance structures. These two are resonance structure. And with the knowing of this, we can able to write with considering both the structure. So alternate double bond or conjugated system. So resonance structure. So with the help of this, he written within the circle. So dotted circle or 6-membered benzene ring. So complete circle or dotted circle, which indicates that the carbon double bonds or pi electrons are rapid movement within the benzene ring. Within the benzene ring. So this is resonance hybrid structure. Resonance hybrid structure. Okay, these two structure what they got. So like this also. So if we saw if each carbon how it will be, each carbon means carbon double bond is nothing but the 3 carbon out of the 6. You can notice here out of 6 carbon and carbon double bond, carbon double bond. So how it undergoes double bond should be sp2 hybridization, sp2 1 s orbital and 2 p orbital. This is how like structure, no, one lobe here, one lobe, and here one lobe. So this is the carbon, and this will be combines with hydrogen. This will be combines with hydrogen now. Similarly, when we take this carbon, this is another carbon, middle carbon. This is second carbon. Right side is another carbon. Exactly 4th, 5th, and 6th carbon. How we can able to write? This is one lobe. This is hydrogen. This is another lobe. Here hydrogen get attached. So here one lobe, here another lobe, here third lobe. Okay, here hydrogen get attached. Similarly, here one lobe, and here one lobe, 3 lobes, right? And hydrogen get attached. So here one lobe, and here one lobe, hydrogen get attached. So from here one lobe, and here one lobe, then hydrogen get attached. So this is how we can able to write sp2 hybridization, carbon carbon double bond, sp2 hybridization, sp2 hybridized structure of benzene. Okay, in that the carbons are sp2 carbon carbon, the sigma bond as well as in pi bond. Each will be left behind with one hybridized p orbital. This unhybridized p orbitals are perpendicular with each other. So this p orbital and this p orbital, this p orbital and this p orbital, here one p orbital unhybridized, here one p orbital, these are perpendicular with each other. This perpendicular with each other, we can able to write one p orbital, here one p orbital, here one p orbital, here one p orbital, and this one, no, this corner here and here. So this above and below in the right side, one p orbital and here one p orbital. If we join this here to here, here to here, and here to here, here to here, and here to here, so how we'll be getting this perpendicular structure? So perpendicular structure of benzene will be getting the Dugnet structure. Dugnet structure of benzene. So a Dugnet structure of benzene, these I'll write here. So same as the benzene means the unhybridized. When I take unhybridized p orbital, unhybridized p orbital. So I'll write here. So in the unhybridized p orbital, so one is here above and here above 2 and here 3 and here 4 and here one fifth one, opposite sixth one. So these are perpendicular. No, this is carbon and this is carbon, carbon, carbon here, and this is carbon, one hybridized. And here is carbon, here is carbon, here is carbon. Okay, so what happened? So here above there will be electron cloud. So above and below there will be double bond, here overlapping, and here overlapping. So we'll be getting pi bond, and pi bond is unhybridized p orbital. So this is with respect to hybridization of sp2, means one s orbital and two p orbital will be forming three hybrid orbitals. Here, no, the three hybrid orbitals. This is one hybrid orbital. So I'll change the color. So here, one hybrid orbital. Here, two, and here, three hybrid. Again, one, two, and three hybrid orbital. What about the blue marked in the blue color? Those are unhybridized p orbital. So I'll show the hybrid, how it will be the hybrid structure. So orbital is, this is, so here we'll be getting, no, this is, you can notice here. So this is sp2 hybridization, right? And sp2 hybridization is 1p orbital, s orbital and 2p orbital will be forming sp2 hybridization. 1s plus 2p, it is equal to 3 hybrid orbital. 1, 2, 3. Similarly, 1, 2, and 3. Similarly, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So each. And hydrogen, 1, 2, 3, 4, 5, 6. So what we got the structure. In this orbital overlapping, which is and the better understanding. This orbital overlapping, you can understand betterly than this when we write the bond line structure. Bond line structure is not understandable. Just we need to think that. So here you will be getting how it is arranged, and these two together, these two are rapid in movement. No, so in unhybridized orbital, p orbital, that is how it forms in lateral overlapping. That lateral overlapping because of unhybridized orbital only. So these are hybrid orbital. These are in this only we can able to write the perpendicular hybrid orbitals. So here perpendicular, here we can write here, and here in perpendicular, here it is in perpendicular. So here you can notice that it is in a perpendicular and here is perpendicular. So this one, if we join in this corner, will be how we are getting like this, here and here the carbon center. Okay, and here one carbon, and here another carbon, unhybridized p orbital. This is another unhybridized p orbital, another unhybridized p orbital, unhybridized p orbital. Now here overlapping pi bond between them, overlapping pi bond between them, overlapping pi bond. So 1, 2, 3. Are you getting? So this is how we are getting the means pi bonds. So this is also we call as Doughnut structure above and below. So if we write like this, benzene ring, okay, above there will be electron cloud. This is above. Below there will be electron cloud. This is above and below. So I'll change the color here. So above, this is an above, and as well as this is an below. So this is what we call as Doughnut structure. Doughnut structure is exactly like uh, in a swim. To in a swimming, we'll be using tire. No, inside the tire. If you hold the tire, if you're jumping inside the water, is exactly like the Doughnut structure. Are you getting? So this is how the Doughnut structure you'll be getting. Okay. Next. So after next is the sixth atom in the carbon, means in the benzene ring are sp2 hybridized. sp2 hybridized means carbon carbon sp2 hybridization, bond angle 120 degree with each other, and these are in trigonal planar structure. So you can notice, no, here this will be trigonal planar structure, this will be trigonal planar structure. Each are the trigonal planar structure with each other, but they are connected with each other. All these are connected with each other. This was a structure given by August Kekulé in 1865 based on the experimental data. So what we are seeing, the diagrams on the screen are the Doughnut means unhybridized p orbital. This is unhybridized p orbital. This is a bonding. Okay. So what I marked in the right here is a bonding above as well as in below, there will be bonding. Similarly, here and above bonding. Here, then be below, there will be bonding. Above and below. So we can have the bonding. We can have the bonding. Okay. So here, okay, this above, here above and below the cloud electron and density. This is what I said, Doughnut. This is what I said, the Doughnut structure. In the middle, carbon, 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 six member. So it's not nice. Here carbon, here carbon, carbon, and the carbon. So this is a path where I have written here carbon, 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 and the above and below, above as well as below. So there will be electron cloud, completely electron cloud, as well as in below. So I can write here and above electron density cloud, here and below the electron density cloud. This is what we call as Doughnut structure. This is what we call as Doughnut structure. So this was given by Kekulé. So these two are not different, both are same. So there will be rapid movement, alternate double bond or rapid movement. That's what they're given. This internuclear distance between all the carbon atoms in the ring has been determined by X-ray diffraction method. From the X-ray diffraction, we come to know that how much, what we got, the length, bond length. This is not a carbon-carbon single bond length or carbon-carbon double bond length. That is in between that. All the 6 pi electrons are 6 pi electrons, 1, 2, 3, 3 pairs, 6 electrons, 6 pi electrons are delocalized. Delocalized can move freely about the 6 carbon and the nuclei of 6 carbon. This can represented in the form of the two Doughnut, two rings or two electron clouds. Two electron clouds, one above, the another one above, one below. In same structure, I have written here, no? So the Doughnut shaped pi, ring shaped pi above as well as below of this benzene. And this we come to know that carbon-carbon single bond length is 154 picometer. And carbon-carbon, the bond length is double bond length is 133 picometer. But what is this? What we are noticing here, no, but this is benzene. In benzene, that is 139 picometer. 139 picometer is lies between carbon-carbon double bonded property, means a bond length, and carbon-carbon single bond length. In between carbon-carbon single and double bond is nothing but partial double bond. In a benzene, carbon-carbon bonds are partial double bond. That is a semi-double bond, not in a complete double bond. Is nothing but it's not a pure double bond. It is a double bond. The double bond are rapid in movement. Is nothing but in each second it's keep on changes. Means one position to another position. From X-ray diffraction method, we come to know that benzene bond length between the two carbon in benzene is 139 picometer. That is in between of single bond and double bond length. Okay, next. This is about the structure of benzene. Next, preparation of benzene. In preparation of benzene, so in alkynes, we studied how the benzene in the chemical equation of alkyne. Okay, so in that the benzene is commercially isolated from coal tar, and it is prepared by in the laboratory by different method. In that, the three important method we'll be discussing. Okay, first one, the benzene is commercially isolated from coal tar, and it may be prepared in laboratory with different process. Okay, the first one, chemical reaction, chemical properties of alkyne. In that polymerization, we studied polymerization, that is cyclic polymerization. Cyclic polymerization, carbon-carbon triple bonded compound, that is ethine. Ethine is passed through red hot iron tube. Already this is we studied. Okay, red hot iron tube, and at 873 Kelvin undergoes cyclic polymerization. This gives a molecular polymerization of the benzene. Is nothing but carbon-carbon triple bonded. No, one carbon. And here is another pair, triple bond. Here is another pair, triple bond. So what happened? This will be shifting here. It forms a double bond. It's one electron pair shift here forms double bond. One electron pair shift here from here to here. Between them, it forms a double bond and single bond. So what happens this? So this we can write. We can write an alternate double bond. So this is the three molecules we can able to write like this: carbon-carbon triple bond, 1, 2, and 3. So if it is double bond, carbon electron shift here, one electron shift here, it forms a double bond and single bond. This is double bond now and single bond. Now one electron shift here. So then what will happen? Between them, there will be single bond and double bond. Between them is single bond and double bond. It forms a cyclic 6-member ring. Cyclic 6-member ring, that is called a benzene method of preparation. So if it donates, it forms single bond. So between them, if it donates, it forms a single bond. Between them, if it donates, it forms a single bond. So alternate double and single bond forms a benzene. Simple method of preparation of benzene. Means cyclic polymerization. Ethine are treated with red hot iron tube at 873 Kelvin gives benzene. That is one of the methods. Similarly, we can able to prepare from decarboxylation. So already we studied decarboxylation. This reactions already based on that only we are studying. Decarboxylation process. Sodium salts of benzoic acid. Sodium salts of benzoic acid is nothing but we need to take a benzene. This is a benzene. In that COOH is carboxylic acid. H is replaced by Na. So sodium benzoate. This will be treated with sodium soda lime, sodium hydroxide or the soda lime. So what it gives in presence of calcium oxide, CaO, upon heating, which gives benzene, gives benzene, and with the formation of Na2CO3, sodium carbonate, along with the formation of hydrogen with the benzene ring. This is replaced by H group, will be getting benzene. So next, second method is method of preparation of benzene. First one is cyclic polymerization, second one decarboxylation. So sodium salts of benzoic acid on heating with soda lime, calcium oxide and sodium hydroxide, mixture of thick lime and the sodium hydroxide is called soda lime. Okay, this will be treated upon heating So which gives benzene and sodium carbonate, and hydrogen can be replaced here on this diagram. You can notice, no? So here COO, NaO, total CO3, Na to CO3 removed, left behind. So here, so COO, Na and COO, this NaO and COO, Na to CO3. Okay, then left behind thing is absence, positive charge. So this will be hydrogen attaches to there, will be getting HHH benzene. Second method. And then the third method is reduction of phenol. C6H5OH is called phenol. Phenol is reduced to benzene by passing the vapors heated over a zinc. When we treat with zinc dust or treat with zinc, so when we treat with zinc, zinc combines with oxygen in that phenol group. So it forms zinc oxide with the formation of benzene. So the three methods of preparation of benzene. First one, cyclic polymerization. Cyclic polymerization. Second one is decarboxylation. Decarboxylation. Third one is reduction of phenol. Reduction of phenol. These are the three methods of preparation of benzene. Okay. Next, we said that aromatic compound. To show aromaticity, there should be condition. There should be condition. So, what are the condition for aromaticity? For aromaticity, the planar, this carbon compound means conjugated pi system. No, that should be a planar and the cyclic conjugated system. In benzene, all the carbon which are present in benzene are in a plane, that is a planar. That is, benzene is a planar molecule. So, planar, a cyclic conjugated system. Cyclic means completely first carbon links to a last carbon. Cyclic will be having conjugated alternate double bonds, means condition for aromaticity. Planar molecule and should be cyclic conjugated system. And the complete delocalization of pi electrons in the ring. In this closed structure, that should be having the delocalization should move. The pi electron should move throughout the carbons from first carbon to a last carbon. Complete delocalization of pi electron in the ring should be takes place. And also it should follow Huckel's rule. Huckels Huckel's rule is nothing but Huckel's rule is called 4n plus 2 pi electron. 4n plus 2 pi electron means the number of electrons in the ring should be 4n plus 2, should follows Huckel's rule. What happened? What is n? N is number of carbon, means number, integer number. N is equal to 0, 1, 2, 3, 4. So what the value it gives, that is the number of electron. So this is also be called as Huckel's rule. If n is equal to 0, integers begin from 0. N is equal to 0, 4 into 0 plus 2 is nothing but the 2 pi electron. E is nothing but one bond. One bond is pi bond formed by 2 electrons. No, so that is one bond. Next, 4, n is equal to 2, n is equal to 1, 4 into 1 plus 2, that is equal to 6. 6 is nothing but, the 6 means 3 electrons, 6 means 6 electrons means the 3 pi bonds, 1 pi bond, next 3 pi bond, next n is equal to 2, 4 2s are 6, 6 plus 2 is equal to 8, 8 means the 4 pi bonds. So to show aromaticity, it should follow the Huckel's rule. 4n plus 2 pi electrons are called Huckel's rule. That is the condition for aromaticity. The compound which will be having, which follows the Huckel's rule, are aromatic compound. So will we see the difference between aromatic and non-aromatic compound. Okay, in that aromatic compound, so benzenoid aromatic compound and non-benzenoid aromatic compound. In this aromatic compound, which follows, few will be having alternate double bond. Even the alternate means conjugated system, but they doesn't consist benzene ring, are called non-benzenoid. If they consist benzene ring, those are we called as benzenoid compound. This should have minimum one benzene ring. So aromatic hydrocarbon should consist minimum one benzene ring are called benzenoid aromatic compound. In that you can see that 1, 2, 3, 3 pi bonds is nothing but 6 electron which follows Huckel's rule, means cyclic planar delocalization of pi electron. Similarly, here alternate 3 pi bonds which follows. Similarly, 1, 2, 3, 4, 5. So 5 pi bonds, 5 delocalization